Attending Jimmy Song's programming blockchain course is an adrenaline rush of knowledge that also fires you up to add to the Bitcoin community. As an alum of the course and in the spirit of contributing, I put together this video as a high-level precursor before diving into the low-level knowledge that Jimmy provides during his course, and I hope you find it helpful. The Bitcoin protocol contains a set of rules that mandate the software component requirements and the data structure requirements for validating the creation, exchange, and storage of Bitcoin on the Bitcoin network. The entire protocol, or individual software components, can be implemented in any programming language, so long as the rules of the protocol are followed. The protocol's rules can only change if there's consensus. If there are changes to the protocol without consensus, then a split or fork of the code implementation occurs. But what does that mean? If there's a change to the protocol that lacks consensus, Bitcoin remains and the changes become something else, an alternative implementation. Bitcoin continues to be used by the community that wants to use it, and the altcoin can then be used by whoever wishes to use it. Bitcoin remains the leading cryptocurrency by most metrics, including market valuation. There have been several forks, including Bitcoin Cash, Bitcoin Gold, Bitcoin Diamond, Bitcore, and more are on the way. A unique characteristic of these forks is that the owners of Bitcoin at the time of the fork are also owners of the new forked currency. This is not the case with platforms like Ethereum that don't share this lineage with the Bitcoin blockchain and therefore do not have an initial shared owners list. The core software components of the Bitcoin network are wallets, full nodes, and miners. Wallets are mainly responsible for holding information necessary to access your coins, to facilitate exchange of Bitcoin through transactions, and interact with the network to derive your balance of Bitcoin. Full nodes are responsible for validating transactions of Bitcoin, validating groups of transactions via blocks, and maintaining a tally of unspent outputs over the network. Miners are responsible for grouping transactions into blocks and then attempting to solve a cryptographic puzzle first in order to add their block to the blockchain in exchange for new Bitcoin and fees for mining the transactions. In order to participate in the Bitcoin network, you have several choices for the components you'll use to own and/or exchange Bitcoin. You can use existing software for all components, use existing software for some components, create custom individual components like a wallet, or if you're really ambitious, create a custom implementation of all the components. The most dominant of the software choices for all components, that is, wallet, full node, and miner, is known as Bitcoin Core and can be found at this GitHub repo. There are also immediately usable binary versions of Bitcoin Core software for Windows, Mac, Linux, and Ubuntu available here. Finally, a wide variety of wallet and mining choices are just a Google search away. So let's look at an actual use case example. Alice wants to transfer 1 Bitcoin to Bob. The Bitcoin protocol dictates that this transfer be done in what's called a transaction. Alice will use wallet software to create the transaction. The protocol data structure requirements prescribe that the wallet separate the transaction into 2 parts, an input and an output. Before we go any further in the validation process, let's do a very quick overview of how keys, signatures, and messages interact, how hashes work, and how full nodes can process certain commands using a language called script. Ultimately, a private key is just a number. The number, when put through a series of computations based on cryptography, produces a public key. Again, the public key is just another number. However, the relationship between the private and public key is interesting. It's easy computationally to derive a public key from a private key, but impossible to derive the private key from the public key. Next, with the private key, I can take a message, in this case part of the transaction, and with the private key perform cryptographic computations on it to produce a signature. More importantly, I can now send the signature, the transaction, and the public key to someone who doesn't know or trust me. They can use the public key to decrypt the signature, which produces a transaction. If the transaction sent is identical to the transaction produced using the public key and signature, the person can know that 1, the transaction hasn't been altered, and 2, that whoever controls the public key was the person who created the transaction. And these features will prove useful in a moment. A hash function, in our case, is a one-way mathematical approach to take data of arbitrary size and transform it into data of a fixed size. If I use SHA-256, a hash function used extensively by the Bitcoin protocol on a transaction, regardless of its size, I'll get a 256-bit number. As long as the information remains unchanged, I'll get the same number each time I hash the original transaction as an input, no matter how many times that I repeat that process. However, if I change even the smallest aspect of the transaction, I'll get a completely different number. This will become useful to assure that the data hasn't changed. In addition, it's impossible for anyone to use the number from the hash to produce the original transaction. Finally, a node contains a stack-based scripting system capable of processing commands from left to right called script. Script was designed not to be Turing complete, meaning, among other things, you can't have loops. Commands contained within a transaction are processed by script to do the validation. Let's head back to our transaction example. Ultimately, the wallet will hash the entire transaction and use the resulting number as a way to identify the overall transaction, called the transaction ID. To construct the transaction, the wallet will decode the Bitcoin address provided by Bob, parsing out a hash version of his public key contained within the address and placing it in the output portion of the transaction. The wallet will then add the amount of Bitcoin specified by Alice to transfer to Bob. Note that Bitcoin can be divided down to 8 decimal places, with the smallest unit being 1/100 millionth of a Bitcoin, known as a Satoshi. An index identifying this particular output is also added to the transaction output. An index is used because there will probably be more than one output. More on that in a bit. So, where is Alice's Bitcoin coming from? The protocol requires that in order for Alice to make the transfer, the wallet must reference a previous transaction ID and index of an unspent output controlled by Alice that contains enough Bitcoin to satisfy the outgoing amount of Bitcoin to Bob. In this case, it's a single unspent output of Alice's that is greater than the amount she is transferring to Bob. You might be wondering where this previous transaction came from. The transaction was part of an earlier transfer of Bitcoin to Alice that was stored in a block on the blockchain. The big picture here is that Bitcoin is transferred via transactions created by wallets. The transaction is then validated by full nodes on the Bitcoin network, and if valid, put into a pool of awaiting transactions. Miners then group transactions together from this pool into blocks and then compete with other miners to solve a cryptographic puzzle. The winning miner's block is validated again by full nodes, and if valid, the block becomes part of the blockchain. The node also updates a running tally called an unspent transaction output, or UTXO. Each transaction has an output, and this tally tracks whether the output of the transaction is referenced by another transaction and is therefore spent and removed from the set, or is a new output that hasn't been referenced by another transaction and is therefore unspent and added to the set. The tally speeds up the process of verifying whether a transaction is valid when it's first created and presented to the network. The remainder of this video will flesh out these steps at a high level. Let's head back to the transaction between Alice and Bob. When we left, we were looking at the reference to Alice's previous unspent transaction that will be the input to her current transaction. The wallet also adds Alice's public key in the input portion of the transaction, and we'll see how this key is used in a bit. At this point, the protocol directs that the transaction must be signed by Alice, and I'm going to go into a very simplified version of the signing process. As with all of the components, Jimmy goes into great detail on how this process actually works. I just want to hit the high points. Essentially, the wallet will take Alice's private key and use it to sign a portion of the transaction's input, along with the transaction's output to produce a signature. This signature is then placed along with Alice's public key as another attribute in the input. Once the wallet has completed the transaction, it will broadcast that transaction to a random full node on the Bitcoin network. The full node will begin validating the transaction immediately. As with signing, I'm going to provide a very high-level look at the process a full node goes through to validate a transaction. The node will look up the referenced output from a previous transaction within a block via its transaction ID. In order to be valid, there must be enough unspent transaction outputs to equal the amount of Bitcoin to be transferred. In this case, the unspent transaction output is greater than the amount being spent. Any remaining bitcoins from an input not specified in the output of the transaction are given to the miner as a transaction fee. So if this transaction were validated with a single output of 1 Bitcoin to Bob, the miner would receive the difference of 1 Bitcoin. Luckily, when the transaction was originally created, Alice's wallet added an additional output to the transaction to a hashed public key that Alice controls in the amount of 1 Bitcoin less a transaction fee to the miner of around 100 Satoshis. In effect, this gives Alice her change back from the transaction. This particular type of transaction is called a pay-to-public key hash transaction, or P2PKH for short. So what are we trying to validate? We want to know that Alice has the right to make the transfer and that the transaction Alice sent hasn't been changed. The full node will use script to process the commands contained in the transaction to perform the validation. To accomplish this, the validating node looks back to transaction 123, where Alice originally received the Bitcoin and obtains her public key hash. The node then hashes Alice's public key within the input of transaction 8983 and compares the two public key hashes to see if they are the same. If they are the same, the node has established that whoever controls the public key in the output of transaction 123 also controls the same public key in the input of transaction 8983. Next, the node will use Alice's public key in the input of transaction 8983 to decrypt the signature contained in the same input and compare the results to the transaction. If they are the same, then we know the person who controls the public key is also the entity that created this transaction. Of course, this is a gross simplification of the validation process. There are many more steps and checks involved, which Jimmy covers extensively, but hopefully this gives you some context. Once validated, the transaction is put into a pool of awaiting transactions on the full node called the mempool. The node will also broadcast the transaction to other random nodes so they can perform their own validation. At this point, we've got a bunch of full nodes on the network that contain a bunch of verified and awaiting transactions. We've established that the protocol can verify the immutability of a transaction, as well as limiting the ability to spend bitcoins to only those that have control over the creation of the public key contained in the transaction output. However, at this point, we don't have a way to prevent Alice from spending the same bitcoin twice, also known as the double spend problem. That's where mining enters the workflow. Mining provides a methodology where an untrusted source can be used to determine the order in which transactions are added to the blockchain. Once we can establish the order in which transactions enter the blockchain, we can simply create a running tally of which transaction outputs haven't been spent. The running tally is known as a UTXO, short for unspent transaction output. Before we get too deep into UTXOs, let's first figure out how Bitcoin provides for ordering transaction in blocks via an untrusted source. Earlier I stated that miners compete with other miners to solve a cryptographic puzzle. Let's examine that cryptographic puzzle in more detail. To review, each miner groups awaiting transactions from a full node into a data structure called a block. The contents of the block, a large random number called a nonce, and the previous block's hash are used as the data inputs into SHA-256. The hash function then creates a 256-bit number based upon those inputs. A dependency across the entire blockchain, from the first block to the latest block, is created by including the previous block's hash as part of the input to the current block. Anything changed in a previous block will be detected because of its cascading effect up the chain. If the miner is the first to get a result from SHA-256 that is lower than a target value set by the network, the miner has solved the puzzle, wins the race, and immediately broadcasts it to the rest of the network. So that's easy, right? Actually, it's exceptionally difficult, and here's why. The hash adds a new random nonce to the input each time the hash is executed, producing a different 256-bit number. Because the target is relatively small in relation to all possible values for a 256-bit number, the likelihood of hashing a number within a target is infinitesimally small. So small, in fact, that the current number of hashes required to return a target number is 8,481,426,187 gigahashes per second for 10 minutes. For reference, a gigahash is a billion hashes per second. So multiply the previous number by 1,000,000,000 and then multiply that times 600, or the number of seconds in 10 minutes, to determine the number of hashes a miner will need to calculate in order to solve the puzzle. The 10-minute figure is a design threshold that the protocol tries to maintain. That is, the protocol wants to produce a block roughly every 10 minutes, and the protocol adjusts the difficulty of the target every 2016 blocks in an attempt to maintain the 10-minute per block average. A large amount of infrastructure is required in both computer hardware and energy to produce the hashes, also called proof of work. Miners commit this infrastructure because of the block reward. If you are the winning miner, you receive 12.5 Bitcoins plus any transaction fees from the block. At the current Bitcoin price, the block reward is a little over $137,000 plus fees per block. So where do the 12.5 Bitcoins for the block reward come from? They're produced out of thin air and form the foundation of the initial money supply of Bitcoin. When a miner creates their group of transactions for their potential block for the blockchain, they add a special transaction called a Coinbase with a hashed public key that they control in the output. The output also contains the 12.5 coin block reward plus all fees from the group of transactions in the block. The Coinbase transaction is a special type of transaction where the input doesn't reference a previous UTXO. Therefore, out of thin air means that the protocol creates new Bitcoin as a reward to the winning miner where none previously existed. Also, the coins rewarded in the output can only be referenced and used within a new transaction after 100 blocks have been confirmed. This reward is adjusted by half every 210,000 blocks, so the current block reward of 12.5 Bitcoins will last about 4 years, and then be adjusted to 6.25 Bitcoins per block, and so on. The protocol also provides for a hard total of 21 million Bitcoins, of which approximately 16.8 million have already been mined. The winning miner immediately broadcasts to the network that they've won. Each full node must now validate the block. Unlike finding the target number, validating the block is much faster. The full node will validate each transaction again, assemble the block, the nonce, the previous block's hash, and hash all of it to determine if it comes up with the target. If it does, the block is validated, and the transactions will be considered to have one confirmation. So the protocol uses keys and signatures to prevent tampering with a given transaction. Mining provides a way for untrusted sources to order the transactions into blocks, which provides part of the mechanism for preventing double spending. The other part of the protocol, which concerns itself with double spending, is UTXO sets. Again, UTXO is short for unspent transaction output. The Bitcoin protocol manages the UTXO set in order to more efficiently account for unspent transaction outputs. Without the UTXO set, a validating node would have to traverse the entire blockchain to determine whether a transaction output was already used. Instead, when a block is validated by a full node, the transaction's unspent outputs are added to the UTXO set, and the spent outputs are removed from the UTXO set. That way, a full node simply has to look to the UTXO set when validating a transaction to determine whether the output referred to in the transaction is unspent. I realize I've covered a lot of material in a relatively short amount of time. My goal is that it provides context for the details that come next. I hope you found it useful, and thanks for watching.